Hello, so today's video we're going to discuss section 7.1, which is integration by parts. We're going to look at how it applies with indefinite integrals and definite integrals by going over a few examples for each of them. So that'll be our first section. We're going to write out a few general rules and formulas for how to go about this. So the idea here is that when we think of product rule, like for differentiation, so product rule states we have d dx, so the derivative of f of x times g of x. So something times something, so the derivative of that we represent by f prime of x times g of x plus g prime of x times f of x. So that's how we do the derivative portion. However, for the indefinite integral, we're going the opposite way. We can rewrite this as f of x times g of x equals integral of f prime of x times g of x plus f of x, or plus g prime of x rather, times f of x. It really doesn't matter which order you go in. And then dx, and then all that is in parentheses. So basically what we're doing here is we're trying to go from the differentiated portion back to the original. And the way we're going to do that, we want to get this, which is the same as this right here. The way we do that is by taking the integral of that whole differentiated portion. So taking the integral of everything that we got after we differentiated. That's the idea of integration. And then for this type of integration, we have to use integration by parts. So we can rearrange this whole thing here as integral f of x g prime of x dx equals f of x g of x minus integral f prime of x g of x dx. And that's the integration by parts formula. So I'm just going to label this and we'll highlight that in green because that's the basic formula we're going to use going forward here. And I'm going to break down how we're going to derive these parts when we actually have an example problem to look at. So to simplify this, we want to pick out a few different parts, and you're familiar with U substitute from Calc 1, so it's basically an expansion of U substitute. So we're going to pick out a part called U, part called V, part called du, and then a part called dv. So we have 4 parts that we're looking for here. So we're going to simplify into 4 parts. And like I said, u, v, du, dv. So we're going to let u equal f of x. And we're going to let v equal g of x. And then we're going to let du equal f prime of x dx, similar to just regular u substitution. And then we're going to let dv equal g prime of x dx. So if we notice, we're given this in any type of integration problem that requires integration by parts, we're given f of x and g prime of x, or something of that sort. Therefore, we automatically know, since we have that, we have our u value, that's right there, and then our g prime of x value, which is right there. So those are coming right from the problem. Now to find du and v, we just either differentiate or integrate depending on which one it is. So that's exactly how we're going to do that. So I'm going to go ahead and label this as our u value, and then g prime of x, that's our dv value. So if we found u, we found dv, then it's pretty easy to find v. We just integrate g prime of x. Likewise, if we have u, we want to find du still, we just differentiate f f of x to get f prime of x. So that's the idea, is it's a process of integration and differentiation of different parts in the problem. Now we want to write this using uv du dv. We would write this exact formula here can be rewritten as integral of u dv equals uv minus integral of v du. So that's exactly, these are exactly the same, this up here, the same exact formula as this, but we're just labeling the parts, and this is what the parts mean right there. So you're probably wondering how we're going to determine which parts are u, which parts are dv. So we're going to remember an acronym called LIATE. So I'll put that in blue actually. So LIATE, and this is going to tell us our choice order. So choice order of which we are to choose these our parts. So first thing we're going to choose is anything with logarithms. Second, we're going to choose inverses. Then we're going to choose anything that's algebraic. Then trig, and then exponents. So basically what this acronym tells us to do is it indicates which parts we should be looking for first, and then saying, okay, is it easier to integrate that or differentiate it, and then assign them appropriately. So if we find something, say a logarithm is easier to differentiate, well then we're just going to select our logarithm as u. So u is going to equal f of x, and that happens to be a logarithm. Then we can take the derivative of that easily. You could do the same thing and make that dv, but then you have to integrate a logarithm, which may be more challenging. So it's always to try to pick which is easiest to differentiate, which is easiest to integrate, and use that as your means of selecting the u value and the dv values. Now we're going to take a look at a couple examples of indefinite integrals that require integration by parts. So the first one, we're going to have, our instructions are just evaluate, and we're given integral of x times sine of x dx. So this requires integration by parts. U substitute cannot work for this. So we're going to say, okay, what is easier to differentiate? What is easier to integrate? Well, let's let u equal x, and then du equals dx. So we differentiate x, that just becomes 1 dx. So that's pretty easy to do it that way. And then we're going to let dv equal sine of x. So that's coming, I'm going to underline in blue where these are coming from, and then this red one is going here. So those are the ones we're pulling right from what we're given. Now we want to find v. So v is just integrating. So integrate sine of x. Well, that should be pretty straightforward from Calc 1 with the integral of sine of x's. So that's just negative cos x. Again, here we're differentiate. So differentiate, integrate. That's the main idea. And now, remember our general formula from the previous page that we went over. We have integral of u dv equals uv minus v minus integral v du. So now we're just plugging in these pieces. So right from our chart that we have established right here. So we see our u value is x and our v value is negative cos x. So we're going to have x times negative cos x minus the integral of v du. So minus the integral of negative cos x dx. Well, we can just bring that negative sign right outside here, get that out of the way. So that'll make this whole thing equal to negative x cos x plus, so this is changing right here, we're combining those negatives into a plus, we're just moving that negative out here. So that's going to be negative cos x plus integral cos x dx. Now all we have to do is take the integral of cos x dx. We know the integral of cos x dx is sine of x from Calc 1. Therefore, all we're doing here, just integrating and then combining this up, and that's our final answer. So we're just left with negative x cos x, compute that integral, we know that to be sine of x, and then add plus c there at the end since this is an indefinite integral, and then that's our final answer for this problem. So again, just a process of integration, differentiation, then putting all the pieces together. For a second example of this type that we're going to look at is going to be to evaluate the integral of ln of x dx. So we want to find our u value, du, and then v, and then dv. So our u value, again, we already have that. In this case, that's just going to be ln of x. So logarithm, that's something that's really easy to differentiate, ln of x. So we're differentiating from that, that's become 1 over x dx. And then our dv value, well, that's just going to be dx because that's all we have left. So just dx, and then if we integrate dx, that just becomes x. So we had something very similar to that in our last problem, where we differentiated x, we got dx. If you integrate x, you get, if you integrate dx, you get x. So we're integrating, and then here we're differentiating. Again, same process. Now that we have all those parts identified, I'm not going to label and break everything down quite as much in this one. Review the first example if you need clarification. But we're going to follow the same process from the first one. uv minus integral v du. So what is uv? So integral ln of x dx equals uv. So what is uv? ln of x times x minus integral of v du. So x times 1 over x dx. Well, at this point, that whole thing is going to simplify down to 1. I'm talking about this because x over x, they just cancel each other out, so it's going to simplify down to 1. So we'll go ahead and write that out here. So we're going to have ln of x times x minus integral dx. At this point, what is the integral of dx? So I just said that earlier, it's x. So right equals ln of x times x minus x plus c, since this is an indefinite integral again, and then that's our final answer for this one. And for the third example of integration by parts to indefinite integrals, we're actually going to apply this process twice. So remember, like L'Hopital's rule, how we had to apply that a couple times. Same thing here. We're going to apply integration by parts twice in order to solve this. So we want to evaluate integral e to the x sine of x dx. Well, same process as before. Pick out our u value from this. So we're going to let u equal sine of x because that's really easy to differentiate. So then du is going to equal cos of x dx. And then our dv value is going to be equal to e to the x dx. And then we know integrating e to the x dx is, we know integrating e to the x is just going to be e to the x. So v is going to equal e to the x. Now we put into that formula uv minus integral v du. So what's our u value? But first we'll just rewrite this. So e to the x sine x dx equals uv. So u sine of x times v e to the x minus integral v e to the x times du cos x dx. If you notice at this point, we still cannot integrate what's on this side, e to the x times cos x dx. We still have to do another integration by parts. So we're going to split this off and put that over to the side. We're going to set up a whole other integration by parts for this part specifically. So we're going to keep sine x times e to the x off to the side. So sine x times e to the x minus integral, and now we're going to break this up again. Remember, we're just focusing on this part for the time being. So we're going to call this u star, so just as it's to keep things straight. So here we'll just let u equal cos x. Du is going to be negative sine x dx, or du star rather. Then dv star is going to equal e to the x dx, and then v is going to equal, or v star is going to equal e to the x. Now that we have our chart labeled with our star values, and this is coming right down from this part right here, we can go ahead and move on to the next part. So we're just applying integration by parts again, so we'll just put a parentheses, and then we're going to say u star v star minus integral v star du star, and then close the parentheses. The reason we had to break this up precisely is because that negative value is going to distribute inside. So that original negative is distributing inside the parentheses. So that's going to affect our signs here a little bit. So we're going to have sine x times e to the x minus what's u cos x v e to the x, so times e to the x. So that negative here again is getting distributed to this term. So minus cos x e to the x. Now that negative is getting distributed here, so that's going to become a positive. So plus integral v e to the x times du negative sine x dx. Well, we can pull this negative here from the sign back out, and then that positive becomes a minus. So go down to our next line. So we have sine x times e to the x minus cos x times e to the x minus integral e to the x sine of x dx. Alright, at this point we can remember that we have our actual problem up here, which is integral e to the x sine x dx, and you'll notice that's the same thing we have right here. So we're actually going to move this down here, and I know we started the equality chain right here, but we're going to restart it. So just to keep things easy, so we have e to the x sine x dx. That's coming right from the start of the problem. This part right here, we're moving it right down there, restarting the equality chain, equals, and then we're going to say this whole thing right here that we finally arrived to. So we're just restarting the equality chain to make things easy. So this thing right here, we're just rewriting. Equals sine x times e to the x minus cos of x times e to the x minus integral e to the x sine x dx. And you might be wondering, well, how are we going to do this? Because this, we're back to where we started at the beginning. Well, we're going to do a little bit of a trick here. We're going to add this whole integral e to the x sine x dx to both sides, e to the x sine x dx. So just like a regular algebra problem, that way we can cancel it out on this side, and then we're adding it here on the left. That gives us 2, because we're just adding. We have our first one here, our second one here. We're adding those together. So we have 2 times the integral e to the x sine x dx equals, and then we're just bringing this whole thing down right there. So it's just like just an algebra problem. We're thinking about this whole part here as a variable. Think of this whole thing here as just variable x. So we're adding x to both sides. That's all that's going on. Equals sine x times e to the x minus cos x times e to the x. And we're going to divide both sides by 2 right there. And therefore we have integral e to the x sine x dx equals sine x times e to the x minus cos of x times e to the x divided by 2. And then that's our final answer right there for this problem. So again, just to recap, we did integration by parts twice. We did it here at the beginning. We got to this point. Then we just preserved everything here, moved it over onto the side. Then we're doing integration by parts a second time for this integral right here. So think about this as just a subproblem. We're calling that the different parts of this star, just so you can differentiate them from the first one. We're redoing that whole process. So we're dropping this down to here, redoing that whole process there. Remember that negative distributes inside the parentheses, this original negative that we had. Redoing that whole integration by parts process right here to get this. Now that we're at this step, just think about this as an algebra problem where we have this is being treated as a whole variable. Now we're restarting the equality chain, so just to simplify things, bringing that down here. So we have this is our original problem equaling this right here, everything we worked up towards at this point. Rewriting it right there. Now we're just taking this tail end, which is what's written there, adding it to both sides. So adding it to both sides, we can cross it off on the right. Now we're left with 2 of these things here. Well, the one we started with and then the one we're adding from the right side, equaling all of this here. Now we just divide by 2 on both sides, cross the 2 out here, then we're left with our original problem, and that's what we're trying to evaluate, is this original problem equaling something, and that something is this right here, which is what we evaluated. This is a very tricky problem, lots of steps to it, but this is definitely one you're going to want to learn how to do. Next, we're going to take a look at definite integrals, doing integration by parts. Now the process is very similar, except now we have endpoints to contend with. So our generic form is going to be integral from a to b of f of x, g prime times g prime of x dx equals f of x, g of x times g of x, evaluated from a to b, minus integral from a to b of g prime of x minus f prime, or g of x minus f prime of x rather, dx. So again, this is just like last time. That's our u, v, minus our integral, and that's v du. So again, very similar to last time. Now we just have the endpoints to contend with. We're only going to look at one example here because the process is very similar. So our first and only example with the definite integral that we're going to look at would be integral from 0 to 1 of tangent inverse of x dx. So we want to identify our u, calculate du. Identify our dv, and then we're going to calculate our v by integration. So what's our u value going to be? We're going to let that equal tangent inverse of x. Differentiating tangent inverse of x is going to be 1 over 1 plus x squared dx. Now remember, from a few sections back, I want to say it was 6.6 or maybe 6.5, we had that whole chart of derivatives and integrals of various trig functions. That is something you're going to need to know, because that's exactly where this is coming from, is that chart. That's something you want to memorize moving forward. We want to do dv. What's dv? That's just going to be dx. So, and then integrate dv is just going to be x. So that one's pretty straightforward. This is just the main one that requires some thought. Okay, just like last time, uv minus integral v du. So we're doing that. We have integral 0 to 1 of tangent inverse of x dx equals tangent inverse of x u times our v value times x evaluated from 0 to 1 minus our integral from 0 to 1 of v du, so x times 1 over 1 plus x squared dx. So this is exactly what we did before, except now the only thing new is we're evaluating 0 to 1 and we have our integral here 0 to 1. It's the only difference. At this point we can simplify. So we have tangent inverse of x times x evaluated from 0 to 1 minus integral 0 to 1. This here we can simplify to being x over 1 plus x squared dx. Now we can't go right ahead and integrate this part. This is not something you can integrate right away. So we're going to need a u substitution. So calc 1, u substitution here. We're going to call it z as our variable. Typically it's u in calc 1, but we already used u up top, so we're calling this z just to keep things straight so we're not confusing anything. So we're going to let z equal 1 plus x squared dz is going to be equal to 2x dx, and then we can say 1/2 dz is going to equal x dx. So now this is just a u sub, so we're going to move everything here down. Now we're going to apply our u substitution that we did right there. Alright, and then we have to make sure we change our boundaries. So we're changing our boundaries from 1 to 2 instead of 0 to 1. So we're just plugging those values into this formula to change our boundaries. The boundaries for this are staying the same. It's just for this integral that we have to change them. So we're left with tangent inverse of x times x from evaluated from 0 to 1 minus integral from 1 to 2 of 1 over z dz. And then that 1/2 we'll go ahead and bring out in front here, actually make things a little bit easier for us. Now we just have to integrate and evaluate. So we're evaluating this part, we're integrating this part. So for our evaluation portion, we have tan inverse of 1 times 1 minus, parentheses, tan inverse of 0 times 0. That's going to all go away because that's equal to 0. So we can kind of eliminate that in our minds. Then we're going to have minus 1/2 times ln absolute value of z evaluated from 1 to 2. So that's just integrating this portion here. We know this term here evaluates to 0, so we can eliminate that. And then we just got to evaluate at from 1 to 2 for ln of z. So we're left with tangent inverse of 1 minus 1/2 times ln absolute value of 2 minus ln absolute value of 1. Well, we know ln absolute value of 1, that evaluates to 0, so we can eliminate that. So now we're just left with tangent inverse of 1 minus 1/2 ln of 2. And we know that tangent inverse of 1 evaluates to pi over 4. Again, look at the graphs if you need assistance with that. But we're going to accept the fact, because this is calculus 2, we're not going over that. But we just need to know that this equals pi over 4, tangent inverse of 1 equals pi over 4. So based on that fact, we have pi fourths minus 1/2 ln of 2. And then that's going to be our final answer for this problem. Again, you might leave it like this if you wanted to, not necessary to go all the way to pi over 4, but that's the smart thing to do, especially if that's what your instructor asks. And that's going to conclude this problem and our topic for today on integration by parts.